Modern utility-scale wind turbines, typically in the 1.5 to 3.6 megawatt class, must operate reliably under highly variable wind conditions. The electrical system manages this multi-megawatt output using a power converter rated for only 30% of the generator's total capacity. This differs from full-scale converter designs, which require larger, more expensive hardware to process 100% of the generated power before it reaches the grid. The Doubly Fed Induction Generator, or DFIG, achieves system efficiencies higher than 94% by utilizing this partial-scale approach. This configuration allows the turbine to vary its rotor speed to match wind conditions while maintaining independent control over active and reactive power. Understanding the mechanics of this 30% power loop is necessary to diagnose the specific electrical and mechanical faults that occur within modern wind farms. The DFIG consists of two primary electrical paths. The stator winding connects directly to the 50 Hz utility grid. The rotor winding connects to the grid indirectly, routing its electrical path through a back-to-back power converter. This converter is divided into three sections: the rotor side converter, the DC link capacitor, and the grid side converter. Slip rings and a brush gear provide the physical electrical connection between the stationary converter hardware and the spinning rotor. Because the stator remains locked to the grid frequency, the DFIG maintains a stable 50 Hz output even as the rotor speed fluctuates with the wind. To maintain maximum energy capture, the turbine constantly adjusts its rotor speed, which requires the converter to inject a controlled current into the rotor windings. In the subsynchronous state, when the rotor spins slower than the grid frequency, power flows from the grid through the converter into the rotor. As wind speed increases, the flow reverses. This is the super-synchronous state, sending power back to the grid. During these transitions, the rotor side converter manages active and reactive power, generator torque, and speed tracking. Simultaneously, the grid side converter regulates the voltage across the DC link and filters harmonics from the output. While this bidirectional flow enables high efficiency, it creates a direct path for grid side disturbances to impact the turbine's internal electronics. Sudden electrical surges often lead to overcurrent faults in the rotor side converter. These faults are typically caused by severe grid voltage dips or sudden wind gusts that create high slip in the generator. Technicians must respond by checking grid voltage stability, inspecting rotor current sensors, and verifying converter temperatures. If a power imbalance occurs between the two converters, it causes the DC link voltage to rise rapidly. Correcting DC link instability requires verifying the braking chopper operation and monitoring the PWM firing commands for the converter switches. Overcurrent faults on the grid side converter are usually linked to external issues like grid imbalance, high harmonics, or a failure in the LCL filter. Because these components are interconnected, a disturbance at the grid level can cascade through the GSC and DC link before impacting the RSC. Faults are not always digital. The physical condition of the slip rings is a frequent point of failure. The accumulation of carbon dust or grease leads to poor electrical contact, which disrupts excitation control and causes rotor overvoltage. Maintenance protocols require replacing these brushes once their thickness drops below 3 to 4 millimeters to maintain a consistent connection. Stator overcurrent is another risk, often caused by insulation faults or short circuits that occur during the high torque of a wind gust. Engineers diagnose these issues by reviewing grid voltage logs and performing a Megger test to check the integrity of the stator cable insulation. Even with advanced control software, the system cannot function if the mechanical connection at the slip rings degrades. The most significant test for a DFIG system is a grid under voltage event, often caused by a fault at a regional substation. Modern turbines must perform a low voltage ride-through, or LVRT. During a voltage dip, the turbine remains connected and injects reactive power to stabilize the grid. An LVRT failure typically suggests a lag in the converter reaction time, a firmware error, or a voltage drop that exceeds the system's hardware limits. Troubleshooting these events requires an analysis of RMS versus instantaneous logs and a verification of the current turbine firmware version. When grid voltage drops, the DFIG's converter logic responds by providing the reactive power necessary to keep the regional grid synchronized. The heat generated during these high-speed power adjustments makes coolant flow and heat sink maintenance critical for long-term hardware survival. Reliable operation requires a combination of vibration analysis, slip ring inspections, and continuous monitoring of grid phase balance. Maintaining the precise operating parameters of the partial scale converter ensures stable power delivery and long-term hardware reliability.